Okay, let's get started. So today, in the first half of the class, we will talk about background knowledge. We covered a lot last week, 2 weeks ago. Today we will finish the background part. Then we will talk about buffer overflow. So you will see examples how you can exploit a program with vulnerability. So the first piece of background knowledge we will cover is system call. So I believe some of you took OS courses. Then in OS class, you design the internal of OS. You program something executed in the kernel mode of the OS. And your OS actually provides service for the applications. And so how can OS provide service to the applications? Those are through system calls. So system call is basically the interface kernel provide to applications. And it is implemented using special instructions. In x86, we use the int instruction because we saw a little bit of the call instruction before. Call instruction is just for the programs to call each other in the user mode or in the kernel mode, but not across the boundary between user mode and the kernel. To cross the boundary, you need to use the special instructions. So if you make a system call, then the CPU enters into the kernel mode, the kernel performs the services, and the kernel eventually returns to the application. So all the application, when they run, the process alternates between executing in the user space and also the kernel space. Usually, when you write a program, you don't directly make a system call. Okay, you make a C library call. And there are a lot of C library wrapper functions. So those functions are basically just a wrapper of system calls. Even the names, they are the same with the system calls names. We're going to say a lot of them later. So on Unix or Unix-like systems, there are usually hundreds of system calls. So the OS provides hundreds of interfaces for the applications. You may already know some of them. Open, read, write, close. So those are system calls to handle a file descriptor, right? Then there is wait, execute, fork, exit, kill. So those are systems calls to send messages to other processes running on the same system. You can wait them. You wait for those processes. You can execute a new process. You can fork the current process, and also you can exit the current. Kill is also the system call to send a message to another process. Like I said, modern OS has hundreds of system calls, and it's still counting. We have more system calls. Windows, some people say probably have 700 system calls. So, like I said, all of you have been programming. So as long as you have been programming, you write programs, the programs run on top of operating system. That program has to make some system calls. But probably none of you had ever directly write a program that make a system call. That's because your program actually only makes a function call to the C library, the libc. And the C library has a lot of functions provided to you, and those functions make system calls. For example, in C library, there is a function called change directory, change dir, and that is a C library function. But under the hood, that C library function will make a system call with the same name, change directory. So if we run a simple program and we use a tool called strace on Linux or Unix, then you can see what kind of system calls this program makes. So this is actually, we can do this on our platform. Let's say we go to any of our challenges here. We go to a simple one, the first the first flag challenge, which just print out the flag for you. So when you go there, you do a strace, and you run this program. Then it will tell you what kind of system calls this program has made so far. So go back to the slides here. This is a very simple program. Let's take a look at this program line by line here. So this program, first flag, has two files. One is a header file, main.c, compiled from two files. Another one is just a header file flag. In the main.c, there is only one function, the main function. The main function call printf first. Printf is a C library function. And we just say, congratulations on getting your first flag. Then we call another library function, which we coded there. It's print flags. And print flags is defined in the flag.h header file. In print flag, we have a local variable, which is a file pointer there. After that, we have a local variable buff, which is maybe 200 bytes, something like that. Local variable. After that, we have a fopen, opens a file called flag under the root directory, and we are only asking for the read permission for that. So if the open is successful, we're going to do another read, fread, read the content of that file into the local variable buff. Then we print out the flag is blah, 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 and that printf will use the local variable. After that, we do fclose. So we close that file. So if it's not successful, we are going to print error cannot open the flag file, right? So this program is very simple. So how many system calls do you think this program will make there? Just look at the program, okay? Very simple program here. Whenever it prints out something, it's probably going to make a system call. When you print out something, your program is sending something to the kernel, then kernel eventually sends that out to the hardware, right? The hardware could be the terminal, everything. Question? What? What's your question? Okay. So printf is not a system call itself, right? But printf, think about this. Your application cannot directly talk with hardware. Your application has to go through the kernel to talk with the hardware. So when you do a printf, your application is actually sending something eventually to your display, which is a hardware. So it has to go through kernel in the middle. And because it has to go through the kernel, it has to make some kind of system call, maybe more than one. So here we can say the main function, there is a printf, that probably will make the system call. Then in print flag, there is open. Open is to open a file in the file system. File system is on a hard disk or any kind of persistent storage. It's not in memory. It's not in the process memory. So you have to go through the kernel loads something from the hard disk to the memory. So that probably will make another system call. Then when you do a fread, actually that's another system call there. So if we go back to the left-hand side of the strace records, you can see all the system calls this program makes when we run this simple program. So the very first system call is actually execve. It's actually executing or replacing the current process with the first flag program. So how many of you took OS class before? Okay, several. So usually in your OS class, the first assignment is to develop a shell, right? You probably developed a shell before. So how do you develop a shell? How does a shell work? A shell will take some input from the user, and that input is what you type in the command line. And the shell will try to execute whatever you input. So what you input usually is a program name or command name. Then the shell itself is a process. It will first fork itself. So there will be two processes. They're both shell. Then one of the process, the new one, the child one, will quickly call the system call execve to replace itself with a new program. And in this case, that is because I type this in a shell, you can see that. I type strace, then the program name. That's a shell. The shell will fork itself, then quickly the new program will call system call to execute the first flag. Then after that, the first flag, the program is loaded from hard disk to the memory. It becomes a process. It's not only a program in rest anymore. Then after that, it makes many system calls. The second one is called access. So this is a system call to check whether a file exists there. Then there is another system called BRK. That's actually break. That is a system call to find out where is the boundary of heap of this program. Then there is arc protection control to set up some architecture-related parameters. After that is F, control file descriptor related to file descriptors. Then several others, you can say open at. There is an open at system call here. Here you can say this is an open at system call. So it's actually very similar to open. This is going to open a file. And you can say what we're opening here. We're opening the C library. This is the libc, C library. So this is how the C library is loaded into the process memory. So after open, we get a file descriptor for that. Then we read it. Then more read. The fstat checks the status of some files. Then we do memory map. So all of this you can see. This piece of program, when we write this piece of program, we didn't make those system calls. Okay? Those system calls were there because the C library, the start main, those functions make the system calls. What maps to our system call is starting from here. This write. This system call corresponds to this printf. So in this printf, we say, congratulations on getting your first flag. Eventually, the program makes a system call, is a write system call, write to the file descriptor 1, right? So in Linux, the file descriptor 0 is reserved for std standard input. 1 is reserved for std out, standard output. In this case, input and output, they both map to the terminal. That's why in the terminal, you say this string, because we are sending out to the standard out, which is a terminal in this case. So after that, the system call returns. And the return value is 45, which is the number of bytes we write to that file descriptor. After that, we use another system call open at. We used this before. We use this system call again. This one, we open the file flag. Here, we were not able to open this file. It says permission deny, okay? So it actually goes to this path. Cannot open the file, so it print out cannot open file, okay? So if we run this program, so you can see here, let's say, so when we run this program with strace, we actually get permission deny here. You are not able to print the flag. But if you run this program directly, you will be able to get the flag. Okay, that's because when you run a program with strace, the program, even though it's a setuid program, it will not have the root privilege. Okay, make sense so far? So how do we really make a system call? System call is implemented, especially on x86 and 64 architecture. They are implemented as software interrupt. And on this architecture, there is a specific instruction, I should say several specific instructions for interrupt. One is the int instruction, int. And for Linux, we use int80 as the system call instruction. The 80 actually is indexed in the interrupt vector table. You just need to remember, in Linux, we always use int 80. Recently, well, maybe has been 15 years, Intel introduced a new instruction called syscall instruction. It's just a syscall. And that instruction also makes a system call. So if you want to know a comprehensive list of system calls on Linux, you can go to this website. They list the system calls provided by Linux, especially in different architectures. Let's say this is a 32-bit Intel machine, and there are a system call exit has a number 1, and we also use other registers to pass parameters to the kernel. And this table shows you what other parameters. For example, the read system call, it has a system call number 3. Then when you make a read system call, you have to put number 3 in the register EAX. Because when you make a system call int 80, the system call number is actually specified in the register EAX. There is nowhere to say, especially at battery level, nowhere to say, I want to do a read. There is a string read. No, there's no such concept there. Then in the EBX, we will have the file descriptor. In ECX, we will have the buffer in the user land where we want to put whatever we read from the hard disk. Also, EDX, we will have how many bytes we want to read. So that is basically the parameters for the read system call. So then let's do a little challenge here. There are maybe 10 instructions here. And let's guess what these 10 instructions do. We are using Intel syntax here. The first instruction is XOR, EAX, EAX. So XOR is exclusive OR. So this instruction will perform an exclusive OR operation on the register EAX. So what will be the output, the outcome of this? So when you do an exclusive OR on the same thing, what do you get? You get 0, right? So basically, this instruction is equivalent to move EAX 0. Move the 0 into EAX. So the first one, we set EAX as 0. Then we push EAX. We said before, push is to push something onto the stack. Then after that, we push some strange values there, 6873, 2F, 2F. I put the ASCII table here. If you check, 68 hex is D, right? 73 there is actually I. 2F is actually the forward slash, right? So you're actually putting some characters onto the stack there because you are doing push. After that, we move ESP to EBX. ESP points to whatever we just pushed there. So yeah, we are pushing something onto the stack, which is on memory. Then that address is in ESP, and we move ESP to EBX. Then we push EAX, we push EBX again, move ESP to ECX. Then we move B in hex into AL. Okay, so B is 11, right? So I'm moving number 11 into the register AL. If you remember from last class, AL is the least significant 8 bits of the register EAX. We already set EAX as 0. Now we are moving just the number 11 to AL, which means the whole EAX register will have the value of 11. Then after that, we make the system call int 80 in hex. So let's visualize this to say what this piece of code is really doing. The first instruction, exclusive OR EAX. So on the right-hand side, I have the stack. We assume ESP points to here. And higher address is at the top, lower address is at the bottom. At the very first instruction, are we going to touch the memory? No, right? It's just a register. We're going to change EAX to 0. So nothing will be touched there. Then after that, we are pushing EAX. Then the value of EAX will go to the stack. Then EAX will point to whatever the value we put there. And the EAX actually has a value 0. After that, we are putting those two numbers there. After that, we move this ESP to EBX. After that, we push EAX. So if we go back to this table, this is 32-bit, you can say number 11, the system call number 11 is actually the system call execute a new program. So this piece of assembly is actually executing a new shell. That's it. That weird string you look at here is just /bin/sh, and the address of that string again and a 0 there. So that's a system call. So for 64-bit, the system call numbers are reshuffled. I don't know what was the design rationale to reshuffle this, but you can say read has a system call number 0, write has a system call 1, 11 is for the system call memory unmap. They are reshuffled. So if you want to make a system call, you need to go to those tables to say what other system call numbers you want to use. So for 64-bit machine, if you want to the same system call, the system call number is not B in hex or 11 in decimal anymore. The system call number is 59. So to make the same system call, you need to use those instructions. And we're not using int 80 anymore because we can still use int 80. However, for 64-bit, there is a special instruction called the system call instruction. This new instruction is available to do that. So we will revisit this part in 2 weeks, where you need to write those, we call them share code. But for now, just give you a high-level feeling what assembly level, what it looks like to make a system call. If you want to learn more about Linux programming, I recommend this book, Linux System Programming. Also in our department, we have 210 or 220 system programming course. That course is talking about how to use C library functions, how to use the functions provided by Linux, and most of those functions, they map to some kind of a system call. So after system calls, we also need to know a little bit about environment and shell variables. So environment and shell variables, they are a set of dynamic named values stored within the system, and applications can use them. So they take this kind of format, a key equals some value. The value can be a string, it can be a number, but even if it's a number, it's actually a string there, right? And the convention is we use uppercase for the keys. And if you have multiple values, they are separated by column. And there should be no space around the equal symbol. So if we go to our platform, we can say what kind of environment variables we have. Then we just use the command env. Then we can get all the environment variables we have here. So the shell This is the name of the environment variable, and we're using bash here. So all of these, they are actually just the strings. The host name, current working directory, there are many other environment variables here. Because this is actually a Docker image, there are not so many. If you have your own Linux system, you do this, you may find many more environment variables there. The reason I cover this is because in one of the hacking challenges, we are going to put the malicious code or share code in environment variables. Environment variables, they are available system-wide and are inherited by the child processes. Share variables are variables that only apply to the current share instance. So that's the difference. Those are the common environment variables. You don't need to remember them, but share is a one. So how many of you here use Linux or Unix? Okay. So what kind of shell do you use? You use bash? Okay. So I actually like Zesh much more. I like Oh My Zesh. I feel it's a much better choice. So if the shell environment variable tells you which shell you are using. Path is a list of directories that can be searched when you execute any command. Then there is user, home, those kind of variables. There are some commands here. env, it will list the environment variables. Also, you can use set or unset export to set those. I put them here, but obviously you don't need to remember them. When you need to do something, just Google and also go back to the slides. So what important here is where does environment variables live in the memory space? So this is a figure you saw 2 weeks ago, right? This is a figure of a classic Linux process. And this is a 32-bit machine. The higher 1 GB is reserved for the kernel. The lower 3 GB is used by the application. And at a very low address, we have the code itself, which is the text segment. Then we have the data segment, the BSS segment. We talked about this. The BSS segment actually has uninitialized variables. And they are supposed to be reset to 0. That's part of the C standard. Then we have heap. We have some libraries, like C libraries. On top of that, we have the stack. The environment variable actually is part of the stack. It's actually the very top of the stack. So the environment variables are there before you run a program, right? Before you run any program, the environment variables are set at your terminal. Then the terminal, the shell, creates your new program. So what that shell does is the shell will push the current environment variables onto the stack, then give the control to your program. That's why the environment variables actually sits at the very top of the stack. So later we will see examples. Maybe not today. We will see examples, so you can have a more straightforward fittings that. So I think the last piece of background knowledge is L files. So L files the format is very complicated. I will try to cover just part of it because we don't need to understand every bit of it anyway. So L files, the name ELF stands for executable and linkable format. So this is a common standard file format for executable files, object files, shared libraries, and also dumps. in Linux or Unix platforms. You may see many different extension names. On Linux, the extension doesn't really mean much. On Windows, how you can open a file is associated with the extension name. In Linux, it doesn't really mean that much. That's why even for L files, we have many different extensions. Usually .a is for static library. .o is for object file. You saw this 2 weeks ago. KO here usually means this is a kernel object. Also mod could also be a kernel module. Some just use .f. Also binary firmware embedded systems, they usually use extensions like AXF or just a bin. Okay. So one L file contains the program and also the data associated. Also has metadata that describes how a program should be loaded and also executed. So this is the structure of a L file. So this is a file, okay? This resides in the file system. This is not what in a memory. So it always starts with an executable header. And the header always starts with a magic number, which is 7F in hex, then just the letters ELF. So all the L files is like that. For example, let's say, go back to our program platform. So we have this program. This program itself is an L file. It's an executable. If we do a file on this, you can say, tell us this is a 64-bit L file, and it's a setuid program. It is dynamically linked. The interpreter loader is this library, and the hash SHA-1 value is this, and there are symbols. It's not stripped. So if we do a cat, so cat is a command you can say the content of the file, right? If we do a cat, you can say a lot of garbage there, because most part of this L file, they are programs. They are not readable English. They're not characters, right? But there are some readable English. For example, the string, congratulations on getting your first flag. That is a string. Then something here in the middle, they are just they cannot be printed. Their ASCII numbers cannot be printed. But always at the beginning of the program, you can say ELF. Actually, before that, there is 7F. But 7F is not printable. That's why you don't see it. So if we use any other tools to do this, to view this, like hex dump, do we have hex dump? Oh, we do. So we do a hex dump, then this program. Then if we go to the very beginning, you can say 7F is actually the first byte. The second byte is 45, which is the character E. And after that is 4C, which is L. Then 46, which is F. So that is the magic number for L file, the first 4 bytes. So after the header actually has a lot of information. But after the header, usually we have something called the program header, and there are sections and also section headers. So the header has a magic number, 4 bytes, but the magic number and other information actually is 16 bytes. Then the header tells what kind of architecture this file is for, and is this file an executable standalone one, or it's an object file, needs to be linked with other files, or it's a dynamic library. What architecture is this? This is for Intel, or this is for ARM. Versions, and many other things. So there is a tool called readelf to help you understand the ELF files. So if you just do readelf, Then dash H means header on this one. Then it can interpret the header for us. Right? It tells us the magic number is like that. Then this L file is for Linux system V. This is dynamically linked. DYN there, dynamically linked. So right now, most of the executables, their type is dynamic shared object. Very long time ago, we are using the type executable. Most of the programs we say now, they do not have the executable type anymore. So the machine is 64-bit machine. Then it also tells us where is the program header, where is the segment, section header, those kind of information. So then let's quickly go through several concepts, sections, segments. Code and data in an L file or binary, they are logically divided into some chunks called sections. And the structure of each section is different depending on what they have there. Some of them may have code, which is machine code in this case. Some of them may have just data. So this is the section header format. You can see that there is a section name, section type, some flags, section virtual address at the So the type here, as you can see, the type can specify this section can be writable. This section need to be allocated. This section is executable, right? This one is exec instr. So executable instructions, basically. Then the flags means also tells us what this section is. We will skip this. If we use readelf-s, you will say how many sections are there for this program. So this program add is a program you saw 2 weeks ago, the simple addition program. And you can say this program actually has 31 sections. Some of the names may be familiar, like .data section. So that's for global variables. .bss section is for uninitialized global variables. Then there is simple tables like this. Most importantly, maybe this section, .text section. So that is where the machine code is, the binary code is. There are other sections, PLT, for dynamic linking, GOT, global offset table. We actually will talk about those two later. Most important sections, .text section, where the code is. Also .init section, that is the initialization code, where the initialization code is. Usually for library functions, some of the library functions like start main, the C library, because when you program, you only program main function and other functions. All of your function will be called by the main function. But who will call your main function? Someone has to call your main function. The C library has functions to call your main function. And those functions need to initialize the memory and set up the environment. And some of them could go to .init section. Also, after you finish, after your main function return, the program doesn't really disappear right away. The program will go back to the C library function, whoever called your main function, then that C library function need to clean up things, then eventually make a system call to ask the kernel to clean up the memory, right? So for those functions, they may go to .fini, finish. We talked about data section. There is also read-only data section, RO data. For example, the string we just saw, the congratulations on getting your first flag. That is a string. But that string is not supposed to change when the program runs. So that string actually can be put in the read-only data section. The data section is for global variables which may change during the program execution. BSS, we talk about this a lot. That's for the uninitialized variables. Their value should be 0 at the beginning. Then there is a technique called the lazy binding, and it requires the help from several different sections, the PLT section, GOT section, and the GOT.PLT. So basically, when a library is loaded into memory and becomes a process for execution, the dynamic linker needs to resolve references to functions located in shared libraries. So in your Linux box, you are running many different applications. And maybe all of them need to use the standard C library, libc, right? So everyone will call functions in libc, but no one is supposed to change libc anyway. Then from the OS point of view, we can take advantage of that observation. We only put one copy of libc in the physical memory. And all the applications on top of OS will share the same copy of libc. However, every process, they have their own memory space, which is also randomized. So their libc, in their own process, the virtual address of libc, the functions could be different. Physically, there is only one copy. But in each process, they may have a different libc address. So when a program is loaded into memory, the kernel will actually randomize the program itself, but the libc will at a different random address in that program's memory address. Then the program needs to know what is the address for any specific C library function. And that is done by the dynamic linker, or you can call it the interpreter we saw before. That's the job of that. And also, the address of those shared functions, they were not known at compile time because they may be randomized at runtime. So one way to do this is when a program runs, the dynamic linker will try to get every C library's function address. But the problem is the program, the application, may not be calling all the C library functions. And to figure out where those C functions are at takes time. If you, when you load a new program, you resolved all the reference to all the functions in libc, then you only used one of them. Then the dynamic linker actually wasted a lot of time, make your program run a little bit slower, right? So the technique modern system use here is called the lazy binding. So basically, this is kind of like just-in-time binding. Only when you make a function call to a C library, the linker will try to figure out the address of that C library function. Before that, we're not trying to figure out. So if you only make 10 function calls to C library, then we only figure out the address of those 10 functions. We're not going to figure out the other 1,000 C library functions address. And this is called lazy binding. And this is achieved with two sections. One is procedure linkage table, and another one is global offset table. The PRT table, the section, is actually a code section. It contains executable code. It contains stubs of well-defined format dedicated to direct calls from text section to library locations. So we're going to say one example here. Where is my? Oh, I don't have the slides for that, but it's actually on our server. So there is a challenge here called lazy binding, let's say, lazy B here. Let's just do the 32-bit version. So this program is very simple. This program only makes two function calls to printf. The first call to printf and the second call to printf. The C code is just as simple as like that. I don't have the C code here on this machine. I should have put the C code on the slides, but I forgot. Let's do a simple obj dump here, then you can see. We do a simple obj dump here, then you can say this is the main function. The main function basically is just two calls to printf. In this case, printf is the same as puts. Actually, the compiler changed it to puts, which is another C library function. Just that, to printf. So if we debug this program, then you will see something very interesting. So this is also where I want to introduce you to a very important tool we are going to use in this class, which is GDB. Right? So many of you probably already used that before. This is a debugger. So we have GDB here. We set a breakpoint. B means breakpoint. We set a breakpoint as the main function. Now we run this program. R means run. Now we are at the beginning of the main function. We can do a this. Disassemble actually. Then you can say this is a disassembly of this program. So what I want to show you is when we make this call, we make two different calls to printf, right? And we're going to show you that the first time we call it and the second time we call it, we're actually calling into different addresses. The reason is that is lazy binding. The first time we call into printf, the program doesn't really know where printf is. It's going to call into the C library stop to figure out where printf is, then continue call to printf. The second time the C code calls printf again, the program already know where it is, so it will call that directly. So to do that, let's set a breakpoint at here. So okay, now we set a breakpoint at F5, which is this here. Let's also set a breakpoint at 07 here. So if you want to set a breakpoint at a particular address, you need to use B star, then this address. Then we use C to keep running. So now we use C. Now we hit the breakpoint. We do a disassemble again, as you can see. Now this one means where the EIP is. What is the next instruction to execute? So when we do this here, you can see we are here. Let's say we can use, we probably want to go to, so what should we do here? Let me see. So here, we just use SI. SI means step in one instruction. So this is the first time we call this printf. When we do sin, we go to this address. Then we keep doing this. There is a jump. So we do si again. As you can see, we're at this place. Then we're at 40. So here is a jump. Okay. So here we jump to some address 6040. The debugger couldn't figure out what function it is. This is actually the stop, the library to figure out where printf is. So remember, this is the first time we call printf. So we do continue. Now we are at the second call site to puts or to printf. We are here, right? So now if we do si again, we are going to 70, keep doing 42. See? Now after 74, we directly go to the say library function printf or somewhere. The first time, we were not there. It's a different address. So even if you make the same function call twice, the first time and second time is actually different address. That's because of the lazy binding mechanism. Most of this class, it will not influence how we hack binaries, but I still want you to say this. So you want to know more about how to use GDB? I give you a link here. I think we about to, so you can see here, this debugger looks much better. That's GDB with some plugin. We installed that on the server. I don't know. But what we saw just now, this plugin is not working. Anyway, so section view and segment view. The program header table provides a segment view of a binary, and the section view provided by the section header table. The section view of ELF binary is meant for the static linking purpose. The segment view is used by the OS and dynamic linkers. So just get kind of familiar with those concepts. This is a program header format, and you can see that some of the types are similar to what we saw for the segment types. So if you do a readf_l add to that add program, you can see all the program headers and also the segment. You can see the segment here. Previously, we saw 31 sections. Now we only see 9 segments, right? So some of the sections, they are merged into one segment, like the interpreter, the dynamic linking tables, those things merged to one, and some data, they merged this one here. The data, they merged into one. Also, all the code, they merged to one. So .init, PRT, text, fini, those are code. They merged into one segment. Okay, last piece of knowledge, background knowledge is binary analysis tools. In this class, you can use any binary analysis tools. For all the demos, I will just try to use objdump because this is a very simple, free tool. In our platform, for the platform you guys are using, we didn't install anything else. But if you want to use other more advanced tools, you are allowed to do that. There is IDA Pro free version. Ghidra is a tool developed by NSA. It's also free, open source. IDA Pro is still the best one, but it's not open source. It's not free. There is a free version for that, which is enough for this class. Also, there is another tool, Binary Ninja, has been quite popular recently. They actually have a web version of that. You just need to register account on Binary Ninja Cloud or something. Then you can load binary there. For some of the challenges, I may try to use Binary Ninja to show you what's going on. Most of the challenges, I would say, I hope you guys just use objdump because this class is supposed to be baby steps, and I want you guys to use the simplest tool possible. Do not rely on those advanced analysis tools. Strings is a tool that can show the strings in your file. NM is a tool to show the symbols in your file. We will use those tools a little bit. So here we have some commands for GDB. When you need, just refer to this. Okay, so now let's take a break. We come back 6:5, 6:6. Then when we come back, we will start hacking. We will do buffer overflow first. Okay, so today we will discuss stack-based buffer overflow. Also, it's a sequential buffer overflow. This is a classic software security problem, which was identified back in the late 80s. So, as the name suggests, in this attack, an attacker tries to overflow data on the stack in a sequential manner. And we will spend several weeks on this topic. There are several reasons we spend several weeks on this. This is actually the very first software vulnerability discovered, and it influenced our understanding of software security in general, lead to many other software problems. And I will give you an extremely brief history of buffer overflow. Then we will say what information a C program needs when it runs, the C calling conventions for 32 and 64-bit machines, how to overflow local variables, that's what we're going to do today, and also how to overflow the return addresses to execute arbitrary code. That's what we're going to do in the next 2-3 weeks. So the objectives include you need to understand how stack works in 32 and also 64-bit machine, especially for Linux. You will be able to identify a stack-based buffer overflow in a program. Of course, sometimes it's extremely difficult. I'm talking about some simple examples we use in the class and also in the final and midterm CTF. In general, identify a problem like that is extremely difficult or sometimes even not possible. Also, you will learn how to exploit buffer overflows to take full control of the computer. You will write exploits, you will write shellcode. A little bit history about this. This is a type of vulnerability discovered back in the 80s. It's impossible to tell who was the first person discovered this anymore. However, there was a famous incident back in 1988 that a student from Cornell, I believe, Robert Morris, I believe at that time he was a student at Cornell. He designed something we call the Morris worm. And this was the first computer worms, computer virus. And it distributed via the internet and took down a large portion of the internet that time. And Morris was actually convicted for this incident. Of course, Robert Morris has been super successful in his career. Right now, he's a professor at MIT, also one of the co-founders of the incubator One Combinator or something. Yeah, so he's an ACM fellow. He made a lot of contributions to computer systems, computer network, computer theory. But before all of that, he made the first one. But even back then, when Morris was convicted, not many people know how this works. Back in the 80s, this was considered like some dark magic. Okay. Then back in 1996, someone called using a pseudonym, Alpha1, he published an article titled Smashing the Stack for Fun and Profit. And this article was published in Frank, which is an underground hacking magazine. This magazine actually still exists. So some hackers still publish there. Of course, now we have other more influential values, but because many attacks, they first appear in this magazine, this is still a very important value nowadays. So I don't really have the real name for Alpha1, but if you Google deep, you will find who he really is. This is a master read. This is one of the first articles explaining how buffer overflow works. It's probably 10 pages or something. and it can help you understand how this works. So even if this vulnerability was first discovered, the type of vulnerability was first discovered back in 80s, it has been like 35 years or even longer. This is still one of the most serious problems we are facing today. So a lot of research my lab does. We are still trying to prevent this kind of attacks. So here is a list of the most popular vulnerabilities. This was back in 2019, but even today could be similar. You will say, you see the first vulnerability. This is published by MITRE, and this is called the CWE, Common Weakness Enumerate. It will list all kinds of vulnerabilities in software or hardware. So the improper restriction of operations within the bounds of a memory buffer is still listed as the number one. So buffer overflow is actually related to this. You can see many other not necessarily binary software bugs, but web software issues. For example, the number two is cross-site scripting. That is a web security issue. Then out-of-bound rate, it's also one kind of buffer overflow. Then secure injection, use after free, we were also discussing in this class. That's related to heap security, cross-site forgery attacks, integer overflow. So you can say, even though after so many years, it's still a very influential and powerful attack. So for you to understand how it works, we first need to understand the say functions. What kind of information do we need to call a function at runtime? And where are they stored, right? Every function, they have code. After compiled, it's binary, it's machine code. Then to call any function, you need to give some parameters to that function. The function at a C level, C function, it only returns one return value, right? Actually, there are ways to return more values. You can just you can just send an address as a parameter to the C function, and the C function can overwrite that address, and you can use that as a return value. But at the C language level, if we strictly define what is a return value, there's only one return value. Then there are global variables. They are not really inside any function. There are local variables. They are defined inside a function. There could be some temporary variables. And every function has a return address. When the function returns, it needs to know where it's going to return to, where the CPU should keep executing at. There are function frame pointers and also previous function pointers, which we will discuss later. So let's first look at the global and local variables. So variables that are declared inside a function or block are called local variables in C. They can be used only by statements that are inside that function or block. Local variables are not known to functions outside their own. That's a C definition. For global variables, they are defined outside a function. They're not in any function. Global variables hold their value throughout the lifetime of the program, and they can be accessed by any function in the program. The definition of function parameters, which are actually called the formal parameters. So formal parameters are actually similar to local variables. They are actually local variables. Let's say a simple program here. We have a main function and a func function. Also two global variables. The first global variable is named G underscore I. G here means global. It's basically a string, right? So that global variable, G underscore I, is just a pointer in this case. Then we have another global variable, which is not initialized. It's just the char star G underscore U. That is not initialized. So then in the main function, the main function has two parameters here. The first one is the number of argument it received, argc. Another one is it's a pointer to an array, argv. Then we have two local variables, li and lu. One is initialized, one is not. One initialized 10, another one is not. Then we print out the address of the global variable gi and the address of the global variable gu. We just print out the address. We want to say where it is. Then we print out the local variable li and lu. Then we call the function func10. So in this case, 10 is a parameter, right? And the function func takes a parameter, which is p. We print out, then the function func also has two local variables, li and lu. You can see that those two variables have the same names as the variables in the main function. Because they are defined in two functions, there is no conflict. Then in the func, we print out where is p, where is ui, and where is u. That's it. So then let's try to say the address of those functions. What's the name of this? Oh, global and local. So let's say the 32-bit version first. This is a 32-bit version of the program. 20 minutes ago, I told you there is a tool called nm to list the symbol names. You can use this tool to say what symbols are in this program. We're not running the program, we're just reading the L file of the program. And you can see there are so many symbols here. Some of them are actually familiar, right? For example, gi is here, that's a global variable. gu is here, is also the global variable. The main function also here, and we have the offset of those address. But we do not find li, lu there. There are two copies of li, lu, right? It's not here because they're not global variables. They're not external symbols. They're not here. When we run this program, you will see all the address of them. This is 32-bit version. So the gi, gu, they are close to each other. They are global variables. They are at address 56 or something, right? So they are at the kind of like the bottom half of the memory map. So the highest address will be just 8F. The lowest address will be just node 80. The middle will be something like 7F, right? So this one is in the bottom half of the memory. Remember the memory address space I showed you guys. However, the li, lu, they are at a very high address, f something. That's because they are on the stack of the main function and also at the stack of the func function, right? And also here you can say the main function calls the func function. The main function executes first, then it calls the func function, and the stack goes from high address to low address, which means the local variables of the main function, the li, lu in main function, will have a higher address than the local variables, the same name, and the func function. So let's say if that's true. So for main, its address is, the li is at D6, 8C, right? However, for li in a func, its address is at D6, 5C. So it's at a much, like 30 bytes or 40 bytes lower address there. And the P is also, like I said, P is, even though it's a parameter, it's actually also a local variable. So you can say its address is also on the stack. It has a higher address than the local variable of func, but has a lower address than the local variables of the main function. So this is a program to show you where the global variables and local variables are at. The 32-bit version will be very similar. The only difference is the address space is much bigger. We use probably 39 bits for 64-bit machine. We're not using all 64 bits. As you can see, the address basically the address is longer. So for a C program, the code obviously is in .txt section. We already know that. The parameters, they will be on stack or on registers. The previous example I showed you, the P is actually on stack. There are examples I will show you later today. It's on register. It's in register. The return value always stores in a register. 32-bit machine is always stored in the register EAX. 34-bit machine, we store the 64-bit version of that register, which is RAX. Global variables, either data section or BSS section or read-only data section. Local variables, usually on stack. If you want to make it faster, it could be on the register as well. Return address, always on stack. The function frame pointers, we will see later, they are always on the stack. And that is where the problem is. So stack is essentially a scratch memory for functions. They are used in all of the architectures. No matter you are using Intel or ARM, we are using this structure. Usually, it starts from high address and goes down to lower address. At least for most of platforms I have used, it's always like this. Functions are free to push registers or values onto stack or pop values from stack into registers. And in x86 or 64, we use the register ESP or RSP to point to the address of the top of the stack. So that the stack goes from high address to low address. So when we push something, the ESP or RSP actually decrements. The top of the stack is actually at a lower address. For example, when we do the instruction push EAX, what the CPU does is the CPU will decrement the register ESP. Even though in that instruction push EAX, in that syntax, you do not say ESP there, right? ESP is implied there. It decrements the stack, the ESP, then it stores the value of EAX into wherever that ESP points to. The pop is the opposite, the reverse operation. It will store the value at the location ESP points to the register EAX, then increment ESP. I will show you a little bit of animation later. So there are several instructions you need to understand. Push, pop, call, return. Most of those 4 instructions, you need to understand how they work. Okay. Then there are also enter and leave, but they are actually just a compilation of those instructions. So a little bit of animation here to better understand what's going on. The instruction we are about to execute is push EAX or push RAX. Before we execute this instruction, the memory looks like this, left-hand side. This is our stack. Higher on top is higher address, on bottom is lower address. We assume that in memory right now looks like there are 3 values, Z, Y, and X. And the ESP or RSP points to the value X. Now we execute this instruction, then the value in EAX will be pushed to several bytes lower than the value EAX, and ESP will also move down several bytes. If it's EAX, it's 4 bytes. If it's RAX, it's 8 bytes. So pop is opposite. If we have the same thing, then if we do a pop EAX, what the CPU does is to get the value in the memory, which is X, move that value into the register EAX, then increment the value of ESP by 4 or by 8 if we're talking about RSP. So that's just the push and pop instruction. Any questions? This seems very simple, but this is critical, okay? This is critical for you to understand the attack and everything. Then the next instruction is a call instruction. Here we use call EAX, which is an indirect call in this case. So most of the function calls will be a direct call. It will be called to an immediate number. Then here we are calling to a register number, which means where do we call to? We don't really know at compile time. Only runtime, whatever value is in an EAX will be our target. The call instruction is used to make a function call, like the C-level function call. The call instruction works like this. Here, the green part, we have the stack. And the gray part, we have the instructions. The stack, we have the top is a higher address, the bottom is lower address. But the gray part, actually, we flip that. The top is lower address, the bottom is higher address. So let's say right now the EIP points to the instruction call EAX, which means the next instruction we are going to execute is call EAX. Before that, we already push 1 there. The stack looks like this. We have Z, Y, X. So the call instruction does 2 things. It first pushes the address of the next instruction to the stack. Okay? So what is the next instruction? What? Yes, so the next instruction is actually pop EBX. So call will first push that address onto the stack. So the stack where we have ZYX, the address of pop EBX. And because it's a push, the ESP will also move down, right? Then it will move the destination address in that instruction, in this case is whatever in EAX, into EIP. And the EIP is where the CPU continues executing, okay? So the reason we push the next instruction address there is eventually when we finish this call, we need to go back to this program, right? And we need to know where to go back to. And that is the instruction we need to go back to. So this is a call instruction. The next is the return instruction, which is a reverse operation of call, okay? Return instruction will only pop the top of the stack. Whatever that value is, we pop that value to EIP, which means the CPU will continue to execute at that address. Let's say we have the stack like this, ZYX, ESP points to X, EIP points to return. We're going to execute a return. So after we execute the return, the value X will go to the register EIP. That's it. So the CPU will start executing from the address X. So those are the 4 instructions, the most important ones. We do have 2 more instructions, one is enter and leave, but like I said, they're not that important. When you debug the program, when you disassemble the program, you may encounter that, so you also need to know what they are. So enter is basically equivalent to these 3 instructions. Because we use those 3 instructions together very, very often, Intel create a new instruction, enter, to replace those 3 instructions. So they are push EBP, move ESP to EBP, then subtract immediate number from ESP. Okay, we will see later why we are doing this. Then leave is just move EBP to ESP, then pop EBP. Important concept here is function frame. Functions, they use stack to allocate space for their local variables. Their local variables, because a function, when it runs, its local variables can be anywhere, right? So how do we find the address of the local variables? And we actually just use ESP, RSP, or EBP to do that. So those local variables will be placed at a fixed offset to those ESP or EBP. Usually we say a function stack frame starts where EBP points to and ends where ESP points to. Also, there is something called calling conventions, which defines who should handle the parameters, who should clean up the stack. We will say two calling conventions today. The first one is the standard Linux calling convention, and we'll first talk about the 32-bit. In this calling convention, the callers, so in the previous example, we have a main function, we have a func function. The main function calls the func function. In that case, the main function is a caller, the func function is a callee. The caller will push arguments onto the stack and in right to left order. Push them one by one onto the stack. Then it executes the call instruction. And the call instruction, obviously, we already talked about it. It pushes the address of the next instruction after call to the stack, then move the destination to the EIP. The callee will do the following. The callee will push the previous frame pointer, which is EBP, onto the stack, and set up a new frame pointer, which is moving ESP to EBP, then create some space for its own local variable, which is just a subtract some numbers from ESP, then ensure the stack is consistent, then returns. When it returns, it puts the return value then in EAX. We are going to say some concrete examples through it. So in function prologues, the beginning of the function, we say this kind of beginning very often, which is push EBP, move ESP to EBP, then subtract some number through ESI. At the epilogue, the end of the function, we always say move EBP to ESP, pop EBP, then return. We say that a lot. Compiler generates this kind of things a lot. That's why those functions sometimes, those instructions are replaced with enter and leave. Okay, finally, we have a concrete example. Let's see. This is actually the same program we looked at before. We have the main function, we have the func function. So I have a little bit code, the assembly code snippet there for the main function, which is actually the call to the function func. You can see here. So this is in the main function, it calls the function func. And this is the C code of the function func, and this is a binary of the function func. We're going to look at this line by line to understand how it works. So when the main function calls that, let's say, I remember main function calls func10, right? Yes. So let's see. I didn't put. Okay, remember the main function here calls the function with a parameter 10 here. Okay, the disassembly I'm showing you doesn't include this part. Just start from here. It actually starts from here. So when we say that, so main function is a caller, func is a callee. The caller needs to send the parameter 10 to the callee. And we said in a calling convention, we're going to use stack to do that. And it is the caller's job to push the parameter onto the stack. In this case, there is only one parameter, which is 10 in decimal. So what is 10 in hex? A, right? So 10 in decimal is A in hex. So that's why we say there is a push A there. That's actually passing the parameter 10 to the function. And that passing is using stack. Then we're going to call this function. So when we call this function, what happens is the CPU will start executing from here, okay? Not executing continuously here anymore. At the beginning of this function, the func, it will push EBP, move ESP to EBP, subtract something, this is 24 bytes there. Then move the A to this address, and then it will call its other functions, printf, something like that. So this is what the stack look like. I draw this myself. So when a function is executing, the EBP, this also applies to the 64-bit version. It's just change everything to 64-bit register. So the EBP, which is a base pointer, will point something called the saved EBP, is the caller's function frame address, the previous function's address. Then on top of that, we will have the return address where this function will return to. Then higher than that, we'll have all the arguments. There could be more than one arguments. Then below that, there will be local variables. Okay. So let's say in a function, if we use say of instruction like this, move the memory address EBP minus 8 to EAX. What do you think this is doing? What is the address of EBP minus 8? Go back to this figure. EBP points to here, right? Then what is EBP minus 8? Might be some local variables, okay? So this one, EBP minus 8, move to EAX. So we're probably moving a local variable to the register EAX. Load the effective address EBP 28. We are getting, load the effective address is an instruction to just get the address of something. So this one is getting the address of EBP minus 24. So basically, we're getting the address of a local variable. If we are doing some positive indexing over EBP, let's say this one, EBP plus 8. So what does EBP points to again? The previous function's EBP. Then 4 bytes higher than that is a return address. The 8 bytes higher than that will be the first argument. You see? So EBP plus 8 is the first argument. Then EBP plus C is just 12, which is the second argument, right? So that's basically the usage of them. Let's look at one more example. This is a factorial function. We use recursive programming to calculate the factorial of number n here. The main function takes 2 arguments. The first is the name of this program, which is fact. Then the second one is integer. After that, it calls the fact function here. Here, it calls the function fact. And the function fact will print out which number it is calculating. It will print out the address of the parameter here, right? So n is a parameter. We're printing out the address of n. If n is not 1, if n is 1, we return 1. Otherwise, we recursively calling this function fact n minus 1, then times n. So that's the same implementation of this one. Do you guys see it? Yeah, I also. Yeah, there is a 32-bit. Yeah, let's do the 32-bit first. So let's just try a small number like 5, right? So when we try a small number 5, the first time it will call the function factor 5, then function factor 5 will call function factor 4, calls function 3, tier 1. If we call this function, we print out the address, as you can see. So even though C code level, this is only one function, but at runtime, this function is called multiple times. So each time it is called, it has its own function frame there. So the first time we call it, we call fact 5, and we find out the address of that parameter is somewhere 680. The second time we call it, it will have its own stack frame, and it will be at an address lower than previous one. That's why we say address 660. The third time we call it 640, 620. So the stack frame actually in this case is exactly 20 bytes. No, 32 bytes, sorry. That's 20 in hex, which is 32 in decimal, right? So even though this is one C function, every time it gets called, it has its own stack frame. Then another example, very simple, very simple program. Main function calls func, and we're just adding 5 parameters together. The func has 5 parameters, A, B, C, D, E, and add them together, then return. Okay, so use the knowledge I just taught you. Where do you think A, B, C, D, E will be stored? Yes, it will be stored on the stack of the func. And who will push that 1, 2, 3, 4 to the stack? The main function will do that, right? Then let's say the code here. Sorry, 2-bit version. So here we just need to say this part, the func function. Also we need to say here. This is in the main function, we're calling the func function, and the main function is actually pushing all the parameters. And the order is we push the rightmost one, then the leftmost one. So the rightmost one is 5. So we push 5 first, then 4, 3, 2, 1. After that, we call the function func, and the function func, if it wants to use that value, it's going to access the value from the stack, right? And we already know that the first parameter will be the last one pushed by main function, and the first parameter will be at EBP plus 8, right? Because EBP points to the old EBP, EBP plus 4 points to return address, EBP plus 8 actually points to the first argument, right? So now you can see that it's trying to get the value of A here. The value of A is 1 in our case. It's at the address EBP plus 8. Move that address to EDX. Then move another address, which is the second parameter, and EBP plus C, also to EAX in this case. Then add them together. Okay, our goal is to add up all 5 numbers together. Now we already add 2 of them together, and the value is in EDX. Then we load the third one, load that to ENX, then add again. So EDX hold the value of 3 numbers adding together. So eventually we get all 5 numbers, we add them together. But as you can see here, we actually put the value, the compiler here, it put the value in EDX. But as a function, when you returns, you have to put the return results in EAX. That's why you see another instruction here. And the last instruction, and we actually add EDX to EAX. So the return value will be in EAX eventually. So that's the 32-bit version of the calling conventions. So using stack to pass parameters is not the only way we can use. We can also use registers to pass parameters. And the benefit of that is it will be faster. Registers, they are part of the CPU. They're very fast. At the end of the semester, actually, we will learn some cache side channel attacks there. Then you will see the time difference between accessing register and time difference from accessing something in memory is actually noticeable. So to make the function program run faster, we hope we can put more things in the register instead of need to go back to the memory. Then in 32-bit version, we actually have another calling convention. That calling convention the name is fast call. The previous one is called the say declare, say standard. And that one is default. If you do not give a function any attribute, it will be compiled using the default way. Otherwise, you can use the fast call. It will generate a little bit faster program. So in this convention, it will try to, the first argument will not go to the stack. It will try to use the register ECX to pass the argument. And the second argument will use EDX to do that. I do not plan to have a demo for this one. I leave this to you. This is part of the homework. You will need to disassemble this and tell the difference. Next, we're going to look at the 64-bit version of the Intel machine. The 64-bit machine, if you remember, they have many more registers than the 32-bit version. 32-bit version, we only have 8 general registers. 64-bit version, we have 16 or more. Because of that, there are more registers for us to use. We don't have to use stack to pass parameters, which is slow. And for 64-bit version, the calling convention is we just use registers. The first parameter goes to RDI. The second one goes to RSI. That's basically the order you want to use. The compiler where we use. So if we look at, so this is the same C program, 5 parameters, add them together. But this time, we compile it as a 64-bit version instead of a 32-bit version. As a machine we are using physically is 64-bit. Then we go to, what's the name? 5, okay. 5. So now we have the 64-bit version of the program. You can say before the function call here. This is a function call to func. Before the function call, we're not using pushing instructions anymore. We're directly moving those numbers 5, 4, 3, 2, 1 to the registers. RDI, in this case, well, EDI is part of RDI, right? So maybe the first 32-bit is 0 anyway. Then also the last one go to R8. Then after that, when we go to the function, we don't need to retrieve that from the register anymore, stack anymore. We directly retrieve them from the register. But actually, you can see here, this is very funny if you think about this part of code. This compiler is not smart, actually. You see what compiler is doing. First, the value is already in the register, EDI there, right? Exactly. The compiler first move it to RBP-4, which is a local variable address. The compiler actually creates some local variables and move the value from register to there. Then it tries to add them together, then move those values from memory, from stack to register again, right? That's a waste of time. Yeah. That's because when I compile this piece of code, I turn off all the optimizations. As you can see, this program is too simple. If I turn on any optimization, the compiler may just optimize away everything. Okay, it will not even do some simple addition. At compile time, it will compute 1 plus 2 to 5 will be 15. It will just print out 15. It will not even generate a code to actually do that calculation there. So that's a difference between 32-bit and 64-bit. Okay, so finally, we are here. We are going to say the very first attack. This will be your first hacking. We are going to overwrite some local variables. In this case, we're not trying to hijack the control flow. We're only trying to overwrite some data. Okay. So this is our example code. Main function takes 2 arguments. It calls valfoo. I name it valfoo just to signify that there's some vulnerability in that piece of code. In that valfoo, let's say we have 2 parameters. One is an integer I, another is a pointer. In the function, I is assigned to another local variable j. Then there is a local variable buff at C level. It's 6 bytes. Then we do a string copy from pointer p to the local variable buff. Then if j, then we do a if j is not 0, basically, then we will print out the flag. Otherwise, it will print IPT the full. Then the function returns. So when we call the function valfoo, we actually set I as 0 here, as you can see. So at the beginning of this function, I will be assigned to j, so j will be 0. So if you just run this program and do not hack it, it will not take this pass. It will take this pass to print out IPT the full, right? So let's try this. This overflow local. Maybe this is overflow local 1, I think. Yeah, we renamed it. Oh, this runs buffer overflow. Okay, so when you this version, we do not print out anything, I guess. So previous version, it will print out IPT the full, but this one doesn't print out. Let me do a quick check. Yeah, okay. It is the same version, just I need to change this part in the slides. It doesn't print out that anymore. Okay, so any of you say why there is a vulnerability here? Yes. The problem here is we call the C library function called string copy. And a string copy will copy from the destination to from the source to the destination. However, in string copy, this function, you do not specify how many bytes you want to copy. It actually stops when the source has a 0. It will only stop that, which means it can copy only 5 bytes if the 6 bytes is a 0, or it can copy 1,000 bytes if the 1,001 byte is 0. So the string copy is actually implemented this way. The string copy takes 2 addresses. One is the source. The second parameter is the source address. It's not going to change that source address. That's why it's a const. Then it's a destination. It returns the destination address. It has an unsigned I here. Then for if the source, the byte we are copying is not 0, /0 is basically 0 in decimal, hex, whatever. So if it's not 0, it will keep copying byte by byte. That's it. Then after that, it will add a 0 at the new string. So because in C, the string is defined by the end of the string is just a 0. So this is basically a string copy. Of course, some people prefer to write it this way, much shorter, only 3 lines of a C code, but it's the same thing. Okay. So the problem of string copy is, like what you said there, it may copy many more bytes than our memory buffer has, right? So let's look at the Overflow function and see what could happen here. So at the beginning of the Overflow function, Overflow is called by main, right? So main pushed 2 parameters there. The first one is it pushed the Okay, so the main function already pushed 2 parameters onto the stack. The first one got pushed was the second parameter, which is a source address of the string, P. Then the second one is the integer I. In this case, it has the value 0. Then it makes a core function, which will push the return address onto the stack. So this is what the stack looks like right now. There is P, there's I, there's a return address. ESP points to the return address, right? Now, the EIP changed to the beginning of Overflow. We are going to execute instructions in Overflow. The first instruction in Overflow is push EBP. So that's what we're going to do. We're going to push. So the EBP still has a value from the main function. We're going to push that value onto the stack. We call that the old EBP. The ESP moves down, right? The second instruction is move ESP to EBP. Okay, so ESP now points here. EBP is a register. So after this, ESP will not change, but ESP's value will move to EBP as well. So both ESP and EBP points to here now. They'll have this address. Now we subtract some number, which in this case is 24, right? 18 in hex, which is 24 in decimal. So we subtract 24 from ESP. So ESP moves down. EBP is not changed. ESP moves down. Now ESP points to EBP minus 18 in hex. The next one, what we do is we're moving EBP plus 8 to EAX. EBP is here. EBP plus 8 is actually the first parameter, right? It's I, which is 0. We move this one to EAX, to a register EAX. So EAX now will have the value 0. And then the next one is we move EAX to to address EBP minus C. Okay? So you see, this is what that C statement J assign I to J or J equal I, what that assignment does. Which means the variable J is actually at the address EBP minus C. Okay? But now it has a value of 0 as well. After that, we subtract 8 again from ESP. So ESP keeps moving down. Then the ESP right now, the address to EBP is already 32 bytes or 20 in hex. After that, we have another push. Why we are doing push here? Because we are going to make a function call. We will make a function call to string copy. That's a function we are going to call. The string copy has 2 parameters, the destination and the source. So we are supposed to say 2 pushes, right? That's the first push, that's the second push. Okay. The first push will have the, which one first? Source address or? Oh, yeah, source is the first one get pushed. Okay. So what do you think the source is here? So the source is P, is what func get. So that's why the value at EBP plus C, which is the value of P, will be pushed again at the EBP, here, basically EBP minus 20. But this is setting up another function call. Then after that, we need to get the address for the destination. The destination in this case will be EBP minus 12. So here we say this is EBP minus C. So EBP minus 12 will be somewhere here, right? And you can say this is EBP minus 12. 12 is 12 is how many? 18 bytes, right? I'm a little bit slow today. Yeah, 12 is 18 bytes. C is what? C is 12 in decimal. 12 is 18 in decimal, which means from here to here, from the local variable buff to the local variable j, we have exactly 6 bytes. And that's what we ask for in the C code. We ask for 6 bytes above, and that's what the compiler gave us. But not always like this. The compiler can do all kinds of tricks to make the memory aligned with some numbers to make the memory accessing faster. So even if we ask for 6 bytes, the compiler sometimes gives us 12 bytes, 24 bytes. That's possible. But in this case, we can say give us exactly 6 bytes. Then that address is also pushed into, that address moved to EAX, then pushed onto stack here. Then we are making the function call string copy. Okay. So we're not going to say the assembly of string copy. Okay. We already know what string copy does. We're not going to say it's assembly code. We just think about what happened here. So if the string copy is going to copy to this place. Okay. So if your input, the string you want to copy, is smaller than 6 bytes, 5 bytes, it will just cover this place, right? However, if it's bigger, what will happen? It will overwrite the local variable j. More seriously, it can overwrite everything at a higher address. Okay? That's where the attack happens. Today, we only talk about we override this j. Okay. So let's say it doesn't override anything. Then after string copy, it will only write to the buffer. It doesn't overwrite the local variable j, anything else. That's also why we call this it's a sequential overflow. Because the attacker need to sequentially overflow from here to here, right? You cannot arbitrarily just write I or P instead of, and do not touch return or old EBP. You cannot do that. So let's say if we don't have this attack, the input you gave is 5 bytes. It doesn't trigger the overflow of J. Then what happens is the ESP will points to here. Then we add ESP 10 bytes, 16 bytes. Then ESP moves up. Then we will compare 0 with some number. This one is for the print flag compare. We actually compare J here because EBP minus 6 is J. We compare if J is 0, right? If J is not 0, we print flag. If J is 0, then we print PT the full, or the new version, we do not print anything. Right? So that's how the 32-bit version. The 64-bit version is actually similar. The only difference is the registers, the parameters, they are passed by the registers, not on stack anymore. However, the string copy, the J, the value J, and the buffer, they are still on the stack. So when you override the buffer, you can still override the local variable J. Okay. So that's our first attack here. So I should clear this. Let me clear this. Okay. So how do we attack this? If we write 1 byte, previously didn't print out PD the full. Oh, I see. The program is actually the same. I think. Oh yeah. I see what's going on. So this is the 32-bit version, right? So if the argument is not true, if you do not provide any argument, the program will just return. So it will not go to val full, it will not print out IPT the full. That's the reason. It's the same version actually. Okay. So if you give any byte, 1 byte, then that byte will be copied to buffer. It will not cause any buffer overflow. All right? So it will just have a IPT the full. If you give 2 bytes, the same thing. But if you give 5 bytes, 6 bytes, 6 bytes, the same thing. If you give 7 bytes, then the 7th byte will go to the value J, okay? Even though the J itself has 4 bytes, but right now that all 4 bytes are 0. You are only changing the least significant byte, but changing that would be enough. When you change that, you get the flag, right? If you change a little bit more, the value of this byte, it doesn't matter. You can give anything, right? Because you give it anything, as long as it's not 0, the value of J will not be 0. Then it will print out. So you can give a little bit longer. That's okay too. Okay. But what if we give a little bit more here? More than 4 bytes. So we do not only. So let's say this is what the memory looks like, right? J is here. J is here. So the distance between J and the saved EBP is actually 12 bytes. So if we give more than 6 bytes, no, not more than 6, more than 10 bytes. So the buffer is here, 6 bytes. J is here, 4 bytes. Then this part, between the end of J and the beginning of EBP, there are also 8 bytes, right? This is 12, this is 4. So this is 8 bytes. So if you give more, then it will fill this part, okay? But it will not cause any problem because no one is using this part, okay? So we can still put 8 more bytes there. 1, 2, 3, 4, 5, 6, 7. Actually, it should be 7. 8 will trigger a problem. Should we put a 7 there, it will not trigger any problem. But if we put 8 there, what will happen? If we put 8 or more there, what will happen? No, not return yet. Then the old EBP will be overwrite. And that old EBP will be used when the function returns, it will be used in the main function. And it will trigger a segment fault. So see, if we do 8, we still print on the flag, but eventually we trigger a segment fault. If we have more of this, the same thing. We will trigger a segment fault. Okay. So I would suggest all of you to debug this program so you can clearly say what's going on there. So let's try to debug this program. We debug this program buffer. We need to run this program. Let's set a breakpoint at valfoo. I think it's called valfoo. We set a breakpoint there. We need to run this program, and we're going to give it, let's give it 7. 2, 3, 4, 5, 6, 7. The 7 bytes. The value doesn't really matter. So we run it. So R is run. So that 1, 2, 3, 4, 5, 6 is the parameter, command line parameter we gave it. Now we run this program. We are in valfoo. We're at the beginning of valfoo. So we can use the command X to examine what the stack look like. So this we are already at, let's see, we're already at here. So we actually already set up the frame. Okay. So at this point, what EBP should point to? EBP should point to the saved EBP, right? So if we do a $P $EBP, we will get the value of EBP in the register. And the value of EBP, you can say it's this address, D648. That's actually the main functions frame. Then how about EBP plus? Then we examine the memory at we examine where EBP points to. The EBP points to this address. Then what should be EBP plus for? EBP plus 4 is supposed to be the return address, right? So when I do this, we should get from the memory location should be the return address. And we can see this address. It's 5655. It's not the stack. It's actually, you can say the code is this address. This is actually the address in the main function. We do a this main. This should be the address after the call to func, right? Remember this address, 6331. Okay. We go to the main function, and this is our function call to valfoo. And the next instruction of this call is 6331, which is our return address. And that return address is on stack, right? So if we do EBP plus 8, we will get the first parameter, which is I, and 0 in this case, right? See, we got 0. If we do 12, we get the pointer, the source address. I don't know where it is, but it's also on stack. Okay. So where are we? We are here. Now let's go to the beginning. Let's go to the point where we call string copy. We set a breakpoint at where we call string copy. Then we set a breakpoint at where we get back from string copy. So we're not going to look at the code inside string copy. Okay, so we continue. You see to continue. Now we check the stack again. So technically at this point, the stack should remain intact, right? We didn't overwrite anything. So if we check the return address, no, we should check J. J's address is EBP minus 12. J's address is EBP minus 12. Say is 12. So J should have the value 0, right? J still have the value 0. Now how about the buffer? The buffer is EBP minus 18. So right now we haven't done the string copy, so it's just to be some garbage there, right? So you can see if we do a string here, we can say it's garbage. Okay. Now we do this. We call string copy. We continue again. Now we are back from string copy to show you where we are at. We just call string copy here. Now we come back to the val foo. We are here. Now we already override 7 bytes there. So the buffer right now should look like 1, 2, 3, 4, 5, 7. Yes, should be that, because there should be a 0 there. So if we do the string here, we check the buffer again. We use X to examine the memory at this location. We can say that memory location has a string 1, 2, 3, 4, 5, 6, and a 7. Right? The 7 part is actually part of J. So if we examine the value of J, which is at this one, you will say it has the letter 7. If we just want to say the value, hex value, it will be 37, which is the ASCII value of J. If we want to say the 4 bytes of it, we do, should we do G? I don't remember. No, not G. G is 8. G is 8 bytes. We should say 4 bytes. Anyone know? D? What should I wear? D? No. What's 4 bytes again? I'm trying to just read 4 bytes from here. So when I use G, it gave me 8 bytes. What? C? Probably not C. I probably have it on my slides. Let me check. I have some, where is it? I had several, maybe in background? Yeah, here. Let's say exam. I can just use a number, I guess. Maybe just 4. Forward also gave me that. Okay, I don't remember which one should I use. W? W is word. I thought we should use D word. Okay, I should use W here. So when I just want to try to read 4 bytes, you can say that's what we get. The lowest byte, the least significant byte, is 37. 37 is the ASCII number of 7 we put there, right? ASCII table. When we input something, we input it as a character. We input it as the character 7. The character 7 in binary is actually 37 in hex. That's what we get there. Okay. So that's basically the first buffer overflow. Where are we? The 64-bit version, actually the same thing. So you will do that in your homework. Okay, let's see the second challenge. This one, almost the same as the previous one, except that here, J, the predicate is changed. The previous predicate is just J, which means J cannot be 0. So now, we want J to be a very specific number. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so how do we attack this one? How do we get a flag? Any idea? Yes. So what we do is, this is overflow 2. Let's do the 32-bit version. So we give it 6 bytes. Then we should put that number there, right? But how do we put the number there? The number, you see that. The number here, those are not necessarily printable ASCII values. Like let's say 12. If 12 is a printable one, 12 is a new line. It's not printable actually. And also 78. Let's say 78 would be 78 is actually printable. It's X. Okay. So to do this, that's why you need to write a little bit code. For this class, you can just use Python. So this is a command we are going to use here. So the $sign here means this part will execute first and get the result, and this result will be used as a command line argument for the program. Okay. So in this case, let's say we use Python 2 here. If you are familiar with any other script languages, you can use here as well. You don't have to stick with Python 2. We have Python 3 and also maybe Perl here as well. So in Python 2, we just do print. The number we want to print is 1, 2, 3, 4. Right. So you see, when we print this, actually one of them is not printable. Okay. So is this correct? Let's see. This actually may not be correct, right? Okay, let's try this. We also need 6 bytes before, right? So let's put 6 bytes. 1, 2, 3, 4, 5, 6. Okay. Okay. It doesn't work. Okay. Why? Why this is not working? That's right, because of the endianness. So 2 weeks ago, we talked about the little endian and big endian, right? So in little endian, the least significant byte goes to the lower address. In this case here, you can say this string will be copied to the memory, and the beginning will go to lower address, right? So the very first byte will be 1, which is 61 in hex. Then we will have 6 of them. Then 12 will go to the 7th byte. However, the 12 will actually go to the least significant byte of J instead of the most significant byte of J. But in this number, actually 12 is the most significant byte. So what we need to do is we need to swap this. We swap this. This should be correct, right? This will give us a flag. Obviously, you can just ask Python to do this. You don't have to do this byte by byte. You ask, if you ask Python to do this, I think this should work as well. No? Did I miss anything here? Interesting. We may need to debug why this doesn't work if I do this. Should work. Anyway, this one works, right? So if you debug, then you need to figure out why it works. Okay, let's say I think that's all I have today. Okay, that's actually all I have today. I will show you the homework of this week. Homework I already uploaded here. So in this homework, So in this homework, so you are going, the first task, second task, I already showed you how to do that in class. You just need to replicate what I did in class. Task 5 and task 6, the same thing. You just replicate what I just showed you. However, task 4, task 7, and task 8, you haven't seen those binaries. I didn't give you those, I didn't give a demo for those ones. So for task 3, it's in the category of reverse engineering. Okay, in this one, you need to use OBJDump or any other tools you want to use to reverse engineer this program, understand what problem it has, and try to get the flag. Task 6 and so this one I'm not really telling you what kind of it doesn't have a vulnerability. It has a secret you need to find out. It's task 3. Task 7 and 8 will be similar to the overflow I just showed you. However, they are slightly different. You need to reverse engineer to figure out how to crack them. Since this is the first week of real hacking assignment, I suggest you to start early. You may encounter a lot of issues. Okay, start early. If you have any questions, ask me or ask on Slack. We will be there to help you. If you start at the very last day, you probably cannot get it done because this is the first week. You are not used to hacking yet. Later, when you get used to this, probably you will be much more skilled and can finish this soon. Cool. Any questions? Okay, is this still fun or? Okay, cool. See you guys next week.